Hello everyone, I'm Yichen Qian. Today I'm going to talk about my final year project. My topic is about low-density parity check channel coding and its application in the digital video broadcasting system. First of all, let me give you guys a brief summary about what I've done during the research. The aim of this project is to carry out researches about the LDPC's code, as well as its application in the DVB-T2 system. First of all, I went through literature reviews about the LDPC, studied about LDPC's history. In this stage, the process was mainly a tertiary research because of the nature of my research style. I went through websites and read literatures about code to have a vast scope about the LDPC. By further studying about what are LDPC's main features, how the algorithms work, and the computation techniques the code is using, I learned that LDPC code is a type of linear block code. It was invented by Gallagher in 1962, and its performance is close to the channel limit, which is considered as one of the most powerful and robust code in communication area. Next, I did researches about DVB-T2 standard and tried to find the role of LDPC in the system. DVB-T2 is a new television broadcasting standard made by DVB organization, and it improves at least 30% channel capacity than DVB-T standard. For modern systems, high coding reliability is a very important factor. DVB-T2 introduced new technology of modulation and coding, and it takes advantage of use of terrestrial spectrum to deliver video and data service for fixed, portable, and mobile devices. This new coding scheme is same as DVB-S2, the second-generation digital satellite television, by using LDPC coding as the inner coding and using BCH coding as the outer coding. DVB-T2 also introduced other new features based on DVB-T, such as constellation rotation, interleavers coding, and so on, which makes the DVB-T2 send a robust signal that can survive in the high noise level and interference circumstance. Last but not least, I used MATLAB to simulate the LDPC and try to examine its performance with different parameters, then used a DVB-S2 model to simulate the LDPC performance in the DVB-T2 system. Through the simulations, results show that LDPC has high reliability in which provides good performance and meets the demand of modern digital video broadcasting processes. Let me now introduce you to the low-density parity check codes, in which is referred as the LDPC codes in the following contents. Here is some information about the history of LDPC. The LDPC codes were first invented by Robert Gallagher in 1962 during his MIT PhD dissertation. The potential performances of the codes were ignored for over 35 years due to its high computational complexity. Back then, the Reed-Solomon code and convolution code were considered as better error detection and correction code until the discovery of turbo code. Despite the more practical feasibility of these codes, the error control performance was rather acceptable due to the theoretically achievable gap to the channel limits. McKay and Neal, two researchers who were studying why turbo codes could have such good performance, introduced a new class of block codes back in 1999. The new features of turbo codes were introduced. It was soon recognized that the new turbo codes was actually an undiscovered part of the LDPC codes developed by Gallagher years ago. New versions of LDPC codes were produced with further studies. In 1998, Richardson and Urbeke, who introduced the new irregular LDPC codes and have stated that the irregular codes actually outperform regular LDPC codes. LDPC code is a linear block error control code that has corresponding parity check matrix and generator matrix. The name is defined by the nature of its parity check matrix, in which is a sparse matrix, consists of only a few ones entries. The sparseness of parity check matrix H guarantees the minimum Hamming distance since it is proportional to the code rate. Overall, this leads to a low error flow. LDPC also has great contribution to the modern digital communication era due to its high reliability in transmissions. LDPC has good performance with its ability to approach the channel limit, in which it is only 0.3 decibel away from the channel capacity. The LDPC code can be further categorized into two types: regular and irregular LDPC code. The difference is that for regular LDPC, ones on each row or column is a fixed number, whereas it is not a constant in the case of an irregular LDPC. Studies show that irregular LDPC usually outperforms regular LDPC, and noted that column weight greater than 3 is considered essential for a good code. A Tanner graph is a bipartite graph in which could help to express LDPC's property. The nodes are separated into two classes, and edges are used to connect two nodes that are not in the same class. Usually, for LDPC, the two classes are parity nodes and message nodes. Number of edges is equal to the number of ones in the parity check matrix. Here is an example of LDPC 8-4 Tanner graph. For where there is a non-zero entry in the parity check matrix, the corresponding parity node and the message node will be connected. There are two major construction methods of LDPC. The original construction of LDPC was presented by Gallagher. The parity check matrix H has a banded structure. The rows of Gallagher's H are divided into number of sets according to its defined column weight. The distribution of non-zero entries follows the following rules. The rows of first set contains consecutive ones entries from left to right over the column entries. For the remaining sets, non-zero entries are randomly permuted accordingly to the first set's allocation. As a result, every column of H would have ones entry once in each set. Another method of LDPC parity check matrix construction is named after Mackay and Neal. In this method, columns of H are added one at a time, straight from left to right. This process will not stop until all the rows are filled. Weight of columns is chosen randomly in order to maintain certain bit distribution. Complex degree of the decoding process of a code is considered to be one of the most important parameters when deciding whether the code is practically achievable. Same as the turbo code, LDPC decoding is also an iterative process. One of the most commonly used decode methods of LDPC is termed as message passing algorithms. It is named so because its operation can be explained by an iteratively message exchanging process between the bipartite nodes along the edges in the Tanner graph. For some further categorization of different message passing algorithms, types are named depend on the kind of messages passed or type of operations performed between the nodes. The belief propagation decoding method passes messages in which is actually the probabilities that represent a level of belief for the value of a code word bit. The probabilities are expressed in log likelihood ratios. It is also known as the sum product algorithm, as its way of computing message by operating sum and product of the information between nodes. The main idea of this algorithm is to use the log likelihood ratio as input, passing this information between parity nodes and message nodes, obtain and store the new information by calculations based on the previous received information. This process is repeated iteratively until the maximum number of iterations set. Then apply hard decision, or shall say the normalized estimation of all of the information of each node, compare with the threshold and produce the output. Now, let me show you guys the results of my test simulations. First of all, to check the performance of LDPC, I computed a comparison between LDPC Hamming code and encoded transmission. And as shown in the picture here, LDPC has extreme low bit error rate, and the next one is the Hamming 7.4. Lastly is the encoded transmission. Next is to examine and find out the effect of different code rate to the LDPC's performance. My assumption was that with fixed code length, higher code rate mean lower parity bits, hence less capability in error control and requires higher SNR to maintain the BER. The signal curves prove my assumption, as we can see here. With higher code rate, more SNR is required to maintain at the same level of the bit error rate. Then, I try to find the effect of different iterations to the LDPC. As we can see in the figure here, with same SNR value, for less iteration numbers, they appear to have higher BER. The result matches with the assumption saying that the more iteration lead to higher accuracy of log likelihood ratio. As a result, the overall decode process would have better performance and to lead to lower bit error rate. In order to simulate DVB-T2 system, I modified an online DVB-S2 model and used it to approximate the DVB-T2 standard. This model used QPSK for modulations, and it also used BCH as outer coding and LDPC as the inner coding, same as DVB-T2. When I varied the channel's SNR at 1, 5, and 10 decibels, the following constellation of RX signal can be observed. The RX constellation graph as shown here. The transmitted signal points are pretty dense with high signal points congested together. On the other hand, the results of simulation with such complex transmission signal DVB-T2 can still decode with zero error rate. This proves that performance of the DVB-T2 system is pretty robust. To conclude, in this project, fundamentals of digital communication system, LDPC codes, and its role in the DVB-T2 system is studied. Simulations are analyzed and provide support for LDPC as one of the most powerful error control code. With fixed code length, higher bit rate will lead to higher bit error rate due to the decrease of parity bits. The more iterations processed, the more accurate the code is. With same BER for more iterations, less SNR would be required. By observing the results, it proves that with the help of BCH as outer coding and LDPC as inner coding, DVB-T2 is a reliable system in the digital video broadcasting area. Some future work focusing on some parallel decoder for multiple transmission line could be a follow-up to the project, as well as different signal modulation in order to conquer the channel fading effect. Also, some key parameters trade-offs could be one of the most important directions in order to achieve better transmission efficiency and accuracy in the power consumption perspective. This summarizes the video. Hope you have a better understanding about the low-density parity check channel coding and how it actually serves in the modern communication era. Thank you for watching.